it's one of those words that we all know, but is still hard to define exactly, still hard to say exactly what it means. We know that energy is what keeps the universe running, and that without it there could be no life, that nothing could get done. But still, energy is a word, a concept that is shrouded in mystery. What really is this thing, this unknown force we call energy? As we'll see shortly, that's not an easy question to answer. Of course, it's not hard to think of numerous examples of energy at work. The sun, our solar system's driving force, animals in motion, and the movement of cars along a busy street are all examples of energy at work. But what is it about them? What common thread do these examples share which allows us to say that all these very different things are examples of the same thing, that they are all examples of energy in use? Early in the 19th century, this basic question was answered by the brilliant American-born doctor and physicist Benjamin Thompson. Energy, Thompson said, is the ability to do work. Well, that's fine. But even when we know that, we still have to answer one other key question. Exactly what is it that we mean by the word work? Normally, of course, we think of work as using effort to do something, to accomplish some task. Scientists, however, prefer a much more precise definition. They say that work is done whenever a force causes an object to move through a distance. In the example you see on the screen before you, the hand and arm provide the force, and the weight is the object being lifted. When the hand and arm move the weight, work is being done. Well, now that that's settled, and we know what we mean by energy and work, let's take a look at the different kinds of energy. Scientists divide all energy into two basic types. They call one type potential energy, and the other kinetic energy. Potential energy is stored energy. The ball has potential energy. When it falls, it has the second type of energy, kinetic energy. Kinetic energy is the energy of motion, or dynamic energy. It's easy to think of a number of examples of potential and kinetic energy from the world around us. A roller coaster is a good example of potential energy changing to kinetic. The roller coaster cars are pulled up a high first hill. A powerful engine and a series of strong cables are used to provide the energy to lift the cars up the hill. At the top of the hill, the cars have a great deal of potential energy. When the cars go down the first drop, the potential energy changes to kinetic energy. The fuel we put in our cars and trucks is another example of something with potential energy. When we drive our cars, the fuel is burned, and it produces kinetic energy, the energy of motion. In addition to the two basic types of energy, potential and kinetic, scientists also recognize a number of different forms or kinds of energy. Heat, for example, is one of the more common forms of energy we find in the world around us. Electricity is another common form of energy. We can use it to do everything, from driving our power tools to lighting up the world around us. And that brings us to light itself. It represents another form of energy which we call radiant energy. Another form of energy, nuclear energy, is bound in the nucleus of atoms. Scientists hope that someday nuclear power plants such as this one will provide much of the energy that we need. Batteries provide us with another form of energy. They store chemical energy for us. So far today, we've looked at examples of the different types and kinds of energy. Now, let's take a minute to look at how energy is used. The uses of energy, whether it's to move us from place to place, to light our way, or to cook our food or warm ourselves, or for any of the many other purposes to which we put it, all involve one key thing in common, and that's change. The change from one type or kind of energy to another. The water behind a dam has potential or stored energy, and if we want to use the potential energy which is stored in that water to make electricity, it must be changed to kinetic or moving energy. This change from potential to kinetic energy happens when we allow the water to flow through the dam and turn the blades in the turbine, which in turn spin the electric generator. We call such a change an energy conversion. And here's another example of an energy conversion. It's an electric circuit that's made up of a battery, which is connected by wires to a bulb. The chemical energy that's stored in the battery becomes electrical energy when we connect it to the rest of the circuit. And when this electrical energy passes through the bulb's filament, it then becomes both heat energy and the radiant energy we see as light. Many devices around us convert energy. Such energy conversions must take place for work to be done. An engine is a device that demonstrates energy conversions at work. The engines in our automobiles, for example, convert the chemical energy in the gasoline and other fuels that power them into the heat energy that moves our vehicles from place to place. And here we see where another kind of energy conversion takes place. The sun is, in some ways, much like a giant engine. It also is in the business of energy conversions, only this time it's nuclear energy that gets converted into heat and light energy. Green plants, like engines, also make energy conversions. Through the involved chemical process of photosynthesis, all green plants convert sunlight, a form of radiant energy, into the chemical energy they need to live and grow. Our bodies also make energy conversions. They convert food, our fuel, into the heat and chemical energy that keeps us going. An important thing to keep in mind about energy conversions is that most of them are one-way affairs. They can work in only one direction and not the other. For example, we can convert all the chemical energy in the gasoline we burn in our cars and trucks into heat energy. But no matter how hard we try, we can't reverse the process. We can't turn heat energy back into a chemical fuel. Unfortunately, no device converts all the energy available to it into useful work. And where does all the unused energy go? Well, in most cases, it's lost as waste heat, such as the hot waste exhaust gases which come out of the tailpipes of our cars and trucks, and the hot emissions which spew out as byproducts of business and industry. During the last few minutes, we've learned a good bit about that hard-to-pin-down word, energy. We've learned, for example, that it's the ability to do work, and that work is accomplished whenever we use a force to move an object through a distance. We've also seen that there are several types and kinds of energy, and that they must be converted from one form or type to another to do useful work. These are valuable lessons as we look to the future and our ever-growing need to use our energy supplies as wisely and as efficiently as possible.